You are sitting in a room of familiar dimensions. The distance between the walls is measurable. Your body occupies a known volume. Gravity behaves as expected. Light arrives from a lamp or a screen at a predictable speed. Nothing about your immediate surroundings suggests instability. Space feels like a neutral container in which objects exist, separated by distances that grow in a straightforward way the farther out you look. What quietly disrupts this assumption is that every precise measurement made beyond your local environment contradicts it. Distances do not simply extend outward. Time does not pass uniformly across them. The farther you look, the less space behaves like a container at all. According to observations that are internally consistent and repeatedly confirmed, the universe does not scale the way your intuition requires it to. The conflict is not theoretical. It is built directly into the data. The question is not how large the universe is, but what scale even means when the act of measuring it alters the thing being measured. 1. The comfort of local space. You begin with the idea that space near you is representative of space everywhere. A meter is a meter, whether it is measured in your room or between stars. This assumption holds locally and breaks only when observations extend beyond the region where gravity, motion, and time behave almost uniformly. In your immediate environment, Tadthini's belief works because it is reinforced by experience. You can place an object on a table, step back, and trust that the distance between you and the object remains fixed unless something moves. The rules governing length, duration, and motion appear stable. They do not depend on where you stand or when you measure them. Instruments calibrated on Earth produce consistent results when used again a moment later. Nothing in this regime suggests that space itself is doing anything other than passively existing. Physics formalizes this comfort through approximation. Locally, space-time is treated as flat. Curvature exists, but it is small enough to ignore. Gravity pulls downward, clocks tick at nearly the same rate, and rulers maintain their length. This is not an illusion. It is a measurable fact. Over short distances and modest speeds, space behaves as though it is rigid and universal. The contradiction emerges only when you attempt to extend this behavior outward without modification. When astronomers began measuring distances to stars, then to galaxies, they applied the same assumptions. Light was treated as a messenger crossing static space. Distance was inferred from brightness, parallax, and timing, all based on the idea that the intervening space was neutral. Those methods worked until they did not. As measurements reached farther, inconsistencies accumulated. Objects appeared dimmer than expected. Their light was shifted toward longer wavelengths. The shift was not random, it increased systematically with distance. Initially, this was interpreted as motion through space, similar to sound changing pitch as a source moves away. But the pattern did not behave like motion alone. Every direction showed the same effect. No central reference frame resolved the discrepancy. What was being measured was not simply how fast objects were moving, but how the space between you and those objects had changed while the light was traveling. The assumption that space was a fixed background had failed. Distance was no longer a static quantity. It depended on when the measurement began and when it ended. This does not violate local experience because the effect is negligible nearby. Over the distance between you and the moon, or even nearby stars, the expansion of space is too small to detect. Gravity binds systems together tightly enough to overpower it. Local space remains stable precisely because it is not representative of the universe as a whole. The realization forces a separation between local truth and global truth. A meter remains a meter where you are, but it does not remain equivalent when projected across billions of years of cosmic history. The ruler itself is not changing in your hand. The framework you assume it applies to is. This creates a subtle but persistent problem. When you say something is far away, you are combining spatial distance and temporal delay into a single idea. The light you receive left its source when the universe was smaller. The space it crossed expanded while the signal was already in transit. The distance you infer now is not the distance that existed then. As a result, there is no single answer to how far something is. There are several, all correct, depending on how you define distance and when you choose to define it. Proper distance, co-moving distance, light travel distance. Each preserves consistency at the cost of intuition. The comfort of local space survives because your daily measurements never force you to confront this distinction. The universe allows a narrow region where scale behaves simply, where space can be treated as a container rather than an active participant. But this region is not typical. It is a special case carved out by gravity and limited extent. Once you step beyond it through observation, the assumption collapses quietly. Nothing dramatic happens. Instruments still function. Equations still balance. What changes is the meaning of the numbers they produce. Space, it turns out, only feels universal because you are small enough to remain inside the approximation where it pretends to be. 2. Leaving Earth without moving. You do not need to travel to leave Earth's scale. Telescopes already do this for you. When you observe distant objects, you are not seeing them as they are, but as they were. Distance becomes entangled with time, turning space into a historical record rather than a static layout. This entanglement is not metaphorical. Light moves at a finite speed, and every observation beyond your immediate surroundings is delayed by that limit. The moon is seen as it was just over a second ago. The sun appears 8 minutes in the past. These delays are small enough to ignore in daily life, which allows you to preserve the intuition that distance and time are separate. Astronomy removes that convenience. When you look at nearby stars, you are already looking years into the past. Their current states are unknown to you. You infer them by assuming continuity, stability, and predictable change. These assumptions usually hold, but they are not guaranteed. The farther you observe, the more those assumptions become untestable. At the scale of galaxies, the delay becomes tens of millions of years. At the scale of the observable universe, it becomes billions. What you call distant space is not space at all in the present sense. It is a layered archive of earlier cosmic conditions, arranged not by location, but by look-back time. This changes the act of measurement itself. When astronomers measure distance using standard candles or redshift, they are not measuring where something is now. They are reconstructing a relationship between emitted light and present observation. The result depends on a model of how the universe has expanded during the light's journey. The implication is subtle. You cannot point to a distant galaxy and say where it is without specifying when you mean. Its position is smeared across cosmic history. The number you assign to its distance encodes assumptions about expansion, geometry, and the behavior of space-time over billions of years. This is where Earth's scale finally dissolves. On Earth, you can measure distance without referencing time. The two are separable. In cosmology, they are inseparable. Every unit of distance carries a temporal cost. Every image is a fossil. The contradiction emerges when you attempt to picture the universe as it exists now. You cannot observe it directly. There is no instrument that can collect present-time information from beyond your local region. The universe you map is always a delayed one, stitched together from signals emitted under conditions that no longer exist. This does not mean the measurements are unreliable. They are consistent and cross-validated, but they describe a universe that is partially gone. When you see a galaxy 10 billion light-years away, you are seeing it when the universe was less than a third of its current age. Its stars, structure, and surroundings may have changed beyond recognition since then. The farther you look, the more the present disappears. Eventually, you reach a limit where the light you receive comes from a time before galaxies existed at all. The cosmic microwave background marks this boundary. It is not a surface in space, but a moment in time when the universe first allowed light to travel freely. This means that leaving Earth's scale does not require propulsion. It requires patience and instrumentation. Each increase in observational reach pulls you deeper into the past. Space does not open outward. It opens backward. The unsettling implication is that the universe you think you inhabit is not the one you see. The one you see is a sequence of earlier versions, layered by distance and constrained by the speed of light. Earth feels central only because it is where your present exists. Everything else is a record. 3. The solar system as a misleading reference. The solar system appears vast until its dimensions are placed against interstellar distances. Even then, its structure reinforces a false sense of proportionality. Orbits, spacing, and gravitational influence suggest a universe that expands outward predictably, which observations soon contradict. Within the solar system, distance behaves in a way that feels orderly. Planets follow stable paths. Their separations increase gradually. Gravity weakens smoothly with distance, and time flows almost uniformly across the system. You can draw a map of planetary orbits and trust that it will remain accurate far into the future. Nothing about this environment prepares you for a breakdown of scale. This stability is not accidental. The solar system is gravitationally bound. The sun's mass dominates local space-time curvature, overpowering the large-scale expansion of the universe. Within this region, space does not stretch in any measurable way. Distances remain fixed not because expansion does not exist, but because it is locally suppressed. This suppression is invisible unless you know to look for it. From inside the system, there is no indication that the rules governing distance might change beyond its boundary. The solar system therefore becomes an intuitive template. You project its behavior outward and expect larger structures to follow the same logic. Early astronomy reinforced this expectation. Stars were treated as distant suns, scattered through a larger but similar volume. Even when galaxies were identified as separate systems, they were imagined as islands embedded in a greater but still static space. The solar system's internal coherence made this assumption feel reasonable. The contradiction emerges when you attempt to scale the solar system's logic indefinitely. If gravity binds planets to stars and stars to galaxies, it seems natural to assume that larger collections should also be bound in some way. But measurements show that beyond a certain scale, binding fails. Structures do not simply grow larger, they stop forming altogether. Galaxy clusters exist, but superclusters do not behave like scaled-up versions of planetary systems. Their members are not orbiting a common center in stable paths. Many are receding from one another, carried apart by expanding space rather than held together by gravity. This is where the solar system misleads you most. Its clean hierarchy of orbits implies a universe where scale is additive. One system fits inside a larger one, which fits inside a larger one still. Observations contradict this nesting. There is a scale at which the pattern breaks. Beyond roughly a few 100 million light-years, the universe stops behaving like a collection of bound systems and starts behaving like a dynamic metric. Distance increases not because objects move through space, but because the space between them changes. The solar system gives no hint of this transition. Its internal geometry remains stable across time. A meter today is a meter tomorrow. Planetary distances do not encode cosmic history. As a result, your intuition never encounters a situation where distance depends on when it is measured. This creates a perceptual trap. When astronomers speak of millions or billions of light-years, you imagine an enlarged solar system, stretched but otherwise familiar. In reality, those distances are not laid out in a fixed arrangement. They are inferred through light that has crossed an evolving space-time. The solar system's scale also hides the role of time. Planetary orbits repeat. Events recur. On cosmic scales, there is no repetition. Structures form, evolve, and disperse without returning to earlier configurations. Distance measurements become snapshots of unrepeatable conditions. What feels like a neutral reference frame is actually a protected pocket. Gravity shields you from the universe's dominant behavior. The solar system is not a representative sample of space. It is an exception carved out by mass. Once this is recognized, the sense of proportionality collapses. There is no smooth progression from planetary systems to the universe as a whole. The logic that holds locally is not merely incomplete at larger scales. It is inapplicable. The solar system teaches you how space behaves when it is constrained. Cosmology forces you to confront how space behaves when it is not. 4. Stars that refuse to be points. At first, stars seem like discrete objects embedded in empty space. Spectral measurements reveal instead that they are moving away from you and that their speed correlates with their distance. Space itself is not static between you and them. To the naked eye, a star is a point of light fixed against the sky. Its position changes slowly, if at all. This apparent stability encourages the belief that stars occupy permanent locations within a vast but motionless backdrop. Early measurement techniques reinforced this impression. Parallax showed that nearby stars shift slightly as Earth orbits the Sun, confirming their distance while preserving the idea of a fixed spatial grid. Spectroscopy altered this picture quietly. When astronomers separated starlight into its component wavelengths, they found consistent patterns. Dark absorption lines appeared where specific elements absorbed light. These patterns were familiar from laboratory measurements on Earth. What differed was their position. For most stars beyond the immediate neighborhood, the lines were shifted toward longer wavelengths. This shift, known as redshift, is not an interpretive guess. It is a measured displacement that can be quantified with high precision. At small scales, it corresponds to relative motion. Objects moving away stretch the light they emit. The faster the recession, the greater the shift. Applied locally, this explanation works. The contradiction appears when the pattern is extended outward. The redshift does not plateau. It increases steadily with distance. More importantly, it does so in every direction. There is no region of the sky where distant stars and galaxies are systematically approaching you. The effect is uniform. If the stars were simply moving through space, this symmetry would be unexpected. Motion through a static medium produces preferred directions. Measurements do not show them. The simplest explanation that fits the data is not that stars are moving away from you, but that the space between you and them is expanding. This reframes what a star is in relation to you. It is no longer a point located at a fixed coordinate. It is a source embedded in a dynamic metric. The distance between you and the star is not a static number. It changes continuously, even while the light is en route. This change is small for nearby stars. Over the few years or decades it takes their light to reach you, the expansion of space is negligible. The star still behaves like a point. Its position remains meaningful. Your intuition survives. At greater distances, the effect accumulates. Light traveling for millions or billions of years crosses a space that has stretched significantly during its journey. The wavelength shift you measure encodes that stretching. You are not seeing the star's motion alone. You are seeing the history of the space it traversed. This creates an observational inversion. You infer distance from redshift, but redshift itself depends on how distance evolved while being measured. The quantity you want to know is entangled with the process of knowing it. Stars, in this context, stop being markers of position and become indicators of expansion. Their light carries information not just about their composition and age, but about the behavior of space-time between emission and detection. The point-like nature of stars also collapses under scale. What appears as a dot is often an entire galaxy. Individual stars merge into unresolved light, and yet the redshift remains measurable. The object's internal structure becomes irrelevant. Its relationship to the expanding universe dominates the observation. This is not a failure of resolution. It is a shift in what matters. At sufficient distance, you no longer observe objects in space. You observe space acting on objects. The refusal of stars to remain points is not a visual effect. It is a conceptual one. The further you measure, the less space behaves like a stage, and the more it behaves like an actor, altering signals in ways that cannot be ignored. What began as a collection of fixed lights becomes evidence that location itself is unstable. 5. The measurement that changed distance. When redshift was measured consistently across galaxies, distance stopped being a simple geometric concept. Light arriving stretched in wavelength implied not motion through space alone, but the expansion of space between emission and observation. Before this realization, distance was treated as a matter of placement. An object occupied a location, and space connected locations without changing their separation. Motion occurred within that framework. Redshift disrupted this hierarchy. It introduced a measurement that could not be explained by relative velocity alone, without producing contradictions elsewhere in the data. The key observation was proportionality. The farther a galaxy appeared, the greater its redshift. This relationship held regardless of direction. It was not sporadic or dependent on local structure. It was smooth, statistical, and persistent. Distance and redshift were no longer independent quantities. One encoded the other. If galaxies were simply moving through static space, their velocities would eventually approach or exceed the speed of light at sufficient distance. Observations do show effective recession speeds that surpass this limit. This does not violate relativity because nothing is traveling through space faster than light. The space itself is changing. This distinction matters because it alters what distance means. In an expanding universe, there is no single, timeless separation between two points. The distance between you and a galaxy is different now than it was when the light you observe was emitted. Both distances are real. Neither is privileged. Astronomers responded by defining multiple distances. Proper distance describes separation at a specific cosmic time. Light travel distance describes how long the signal took to reach you. Comoving distance factors out expansion to compare positions as if the universe were frozen. Each definition is internally consistent. None restores the simplicity you expect. This multiplication of distances is not mathematical indulgence. It is required to preserve consistency across observations. When you compare supernova brightness, galaxy clustering, and background radiation, the same expansion history must reconcile all of them. Distance becomes a derived quantity, not a directly observed one. The measurement that changed distance also changed causality. In a static universe, if something exists far away, it could, in principle, affect you given enough time. In an expanding universe, this is no longer true. There are regions whose present state can never influence you, no matter how long you wait. Redshift marks the boundary of causal relevance. As space expands, light emitted beyond a certain distance will never reach you. Distance now includes an implicit statement about what can and cannot be known. This reframes observation as a constraint. You do not observe the universe as it is, but as it allows itself to be observed. Expansion filters information. It stretches wavelengths, dilutes energy, and eventually removes entire regions from contact. The unsettling aspect is not the expansion itself, but its measurability. Redshift is not inferred indirectly. It is read directly from spectra. The universe presents its own alteration of distance openly, without ambiguity. Every distant galaxy carries a record of how space has behaved since its light began traveling. Distance is no longer a static separation, but an accumulated process. You do not measure where something is. You measure what happened to the space between you. This undermines the intuition that geometry is fundamental. In cosmology, geometry evolves. The metric that defines distance is time-dependent. Space is not a container. It is an active variable. Once this is accepted, the idea of a fixed cosmic map dissolves. There is no universal coordinate system that remains valid across time. Every map is provisional, tied to an epoch and an expansion model. The measurement that changed distance did not make the universe stranger by adding speculation. It did so by revealing that the simplest quantity you thought you understood was never simple to begin with. 6. Expansion without a center. You might expect expansion to originate from a point. Observations show no such center. Every direction recedes equally. The contradiction is not philosophical. It is mathematical, and confirmed by galaxy surveys that agree regardless of where you observe from. From everyday experience, expansion implies an origin. Objects spread outward from a source. Debris moves away from an impact. Growth has a direction and a starting place. When the universe is described as expanding, this intuition persists, even when it is explicitly denied. Measurements do not support it. When astronomers map the motion of galaxies, they do not find a gradient pointing back to a central location. Instead, they find the same pattern everywhere. Distant galaxies recede. More distant galaxies recede faster. The relationship holds no matter which direction you choose. This uniformity is not inferred from a single vantage point. It emerges from many independent observations. Surveys conducted from Earth, measuring galaxies in opposite regions of the sky, return the same expansion rate within uncertainty. The data does not privilege any axis or location. The mathematical description that fits these observations replaces the idea of motion through space with the expansion of space itself. In this framework, galaxies are not moving away from a center. They are maintaining roughly fixed positions relative to their local surroundings, while the metric between those surroundings changes. A common analogy compares the universe to the surface of an inflating sphere. Points on the surface move away from each other as the surface expands, yet none of them is the center of the expansion. The center exists, but not within the surface itself. It is not part of the space being measured. The analogy is imperfect, but it captures the essential feature. Expansion can occur without a central location inside the system. The universe does not expand into something. It expands by altering the relationships between points within itself. This directly contradicts the expectation that there should be a place you could identify as the beginning. Observations do not show any region from which expansion radiates. The cosmic microwave background, when measured across the sky, shows the same temperature in every direction to high precision, with only small fluctuations. If there were a center, you would expect asymmetry. One side of the sky would look systematically different from the other. It does not. The uniformity is not exact, but the deviations are random, not directional. This forces a re-evaluation of position. If expansion has no center, then no observer occupies a privileged location. Any observer in any galaxy would see the same pattern of recession. The expansion does not single you out. This does not mean that all locations are identical in every respect. Local structures vary. Galaxies cluster. Voids exist. But when averaged over large enough scales, the expansion behaves the same everywhere. The absence of a center is not an abstract claim. It is embedded in the equations that describe space-time and validated by observation. Attempts to reintroduce a center produce inconsistencies with measured redshifts and background radiation. The unsettling implication is that the universe lacks an external frame of reference. There is no viewpoint from which the expansion could be seen from the outside. All observations are internal. This creates a conceptual closure. You can measure how the universe changes relative to itself, but not relative to anything beyond it. Expansion is defined without reference to an external space. The idea that everything is moving away from everything else without a central cause challenges the way you assign meaning to distance and origin. It removes the possibility of tracing expansion back to a location in space. What remains is a universe where change is global but uncentered. Expansion happens everywhere at once. Without a point of initiation you could point to or approach. The contradiction is not resolved by imagination. It is enforced by measurement. 7. Scale begins to slip. As distances increase, the idea of a fixed ruler fails. The same unit length does not preserve meaning across cosmic time. Expansion changes the distance while light is in transit, making the measurement dependent on duration rather than location. At small scales, measurement feels absolute. A ruler laid end to end produces the same result no matter when or where it is used. Time does not enter the calculation. You assume that length exists independently of observation, waiting to be revealed. This assumption survives every local test. Cosmic measurements violate it without warning. When light travels across expanding space, the distance it crosses does not remain constant during the journey. The separation between source and observer increases while the signal is already moving. The result is not an error or distortion. It is the correct outcome of a dynamic geometry. This creates an unfamiliar situation. You are no longer measuring a distance that exists independently of the act of measurement. You are measuring a process. The number you obtain reflects how space behaved over time, not where something is in a single moment. To manage this, cosmology introduces multiple rulers, each valid only under specific definitions. One ruler measures how far away an object was when it emitted light. Another measures how far it is now. Another compares positions as if expansion were paused. None of these rulers contradict the others. They answer different questions. What disappears is the idea that there is one correct length. This loss is not philosophical. It appears directly in data. When astronomers compare distances inferred from supernova brightness with those inferred from background radiation, they must account for how scale evolved between those epochs, ignoring that evolution produces measurable inconsistencies. The slipping of scale also affects density. Matter that appears densely packed in the early universe becomes dilute over time, not because particles move apart through space, but because space itself grows between them. Density becomes time-dependent in a way that has no local analog. This undermines another intuition. You expect that if two objects are far apart, they must have moved to get there. On cosmic scales, separation can increase without motion. Objects remain locally at rest while their distance grows. The ruler you imagine stretching between them stretches as well. Because of this, scale cannot be detached from time. 1 billion light-years does not describe a fixed length. It describes how long light has been traveling under specific expansion conditions. Change the expansion history, and the same redshift implies a different distance. This dependence forces cosmology to treat scale as a model-dependent quantity. You do not measure distance directly. You infer it by fitting observations to an evolving space-time description. The inference is constrained, but it is not absolute. The further you push outward, the more pronounced this effect becomes. Nearby galaxies allow approximate agreement between different distance definitions. At high redshift, those definitions diverge sharply. What once felt like minor technical distinctions become dominant. This is where intuition finally fails. You cannot visualize a ruler whose length depends on when you use it, yet this is exactly what the universe requires. Space does not provide a fixed grid. It provides a changing one. The slippage of scale also limits prediction. You can extrapolate backward to reconstruct earlier sizes, but you cannot assign a timeless dimension to the universe as a whole. Its size now is not directly observable, and its size then depended on conditions that no longer exist. Scale becomes relational rather than intrinsic. It describes how regions compare to one another across time, not how large they are in isolation. What remains stable is not length, but law. The equations governing expansion remain consistent, even as the meaning of distance shifts beneath them. Measurement survives, but certainty about scale does not. The failure of a fixed ruler is not a flaw in observation. It is a property of the universe that only becomes visible when you measure far enough for time to matter as much as space. 8. The observable universe is not the universe. What you can see is limited not by space alone, but by time and the speed of light. The observable universe is a boundary defined by causality, not by an edge. Beyond it, scale becomes undefined by observation. This distinction matters because it separates existence from accessibility. The observable universe is not a container holding everything that exists. It is the region from which light has had enough time to reach you since the universe became transparent. Its boundary is not marked by matter or structure, but by the limits of signal transmission. You do not see space as it is arranged now. You see only what has been able to communicate its state to your location. This communication is constrained by two factors: the finite age of the universe and the finite speed of light. Together, they impose a horizon. This horizon behaves unlike any boundary you encounter locally. You cannot approach it, you cannot cross it. No matter how long you wait, light emitted from beyond a certain distance will never arrive. The horizon is not static, but it is also not receding in a way that allows access. It is defined by expansion itself. This creates a paradoxical geometry. The observable universe has a finite radius, yet the universe may be much larger, possibly infinite. Observations cannot distinguish between a very large finite universe and an infinite one beyond the horizon. Both produce the same measurable region. The horizon is therefore not a wall, but a cutoff in causality. Events beyond it are not hidden behind something. They are disconnected. Their present state cannot influence you, and your present state cannot influence them. This has direct consequences for scale. Inside the observable universe, distances can be defined, modeled, and compared. Beyond it, distance loses operational meaning. You can assign numbers using extrapolation, but those numbers cannot be tested or verified by observation. This does not mean the region beyond the horizon is fictional. It means it is physically inaccessible. Its properties may follow the same laws, or they may not. Observations cannot decide. The cosmic microwave background marks the furthest surface you can observe directly. It is often described as the edge of the observable universe. But it is better understood as the earliest moment light could travel freely. Beyond that moment, the universe was opaque. Before it, photons could not move unimpeded. This means that the boundary you observe is temporal as much as spatial. You are not seeing the farthest place. You are seeing the earliest time. The observable universe, therefore, encloses a volume that is not representative of the whole in any guaranteed way. It is a sample constrained by causality. You assume that the laws measured here apply everywhere because they do so consistently within this region. That assumption is reasonable, but it is not provable. Scale becomes ambiguous at this point. You can calculate how large the observable universe is today, taking expansion into account. You can estimate how large it was when the cosmic background radiation was emitted. But you cannot assign a total size to the universe itself without stepping beyond observation. This limitation is not technological. It is structural. No improvement in instruments can overcome the horizon imposed by space-time expansion. Even perfect detectors cannot receive signals that never arrive. As expansion accelerates, the horizon tightens. More regions that are observable now will eventually cross out of causal contact. The observable universe is not only limited, it is shrinking in terms of accessible information. This introduces an asymmetry between existence and knowledge. The universe may continue indefinitely, but your observational reach does not. Scale can increase without increasing what you can know. The unsettling implication is that cosmology operates within a permanent blind spot. Its most fundamental questions concern a totality that cannot be fully measured. The observable universe is all you can work with, and it is explicitly not all there is. What lies beyond the horizon is not distant in the usual sense. It is unreachable in principle. Scale beyond that boundary exists without reference to you, unmeasured and undefined by any possible observation. 9. A horizon that is not a wall. The cosmic horizon behaves unlike any physical boundary. Objects beyond it are not blocked, they are disconnected. Their light will never reach you, regardless of how long you wait, because space expands faster than signals can cross it. In everyday experience, a horizon is something you approach. A mountain blocks your view. A wall stops your movement. Given enough effort, you expect to reach it or go around it. The cosmic horizon does not allow this intuition. It is not located at a place you could travel toward. It is defined by the behavior of space-time itself. This horizon emerges from a simple constraint. Light travels at a finite speed, and space between distant regions is expanding. When expansion is slow, light can cross increasing distances and eventually arrive. When expansion is fast enough, the distance grows more quickly than the light can close the gap. The signal falls behind permanently. This is not hypothetical. Measurements of distant galaxies show that many are already receding from you faster than light, when their distance is defined in present terms. This does not violate relativity, because nothing locally outruns light. The separation increases because the space between you and the source is stretching. The horizon marks the threshold where this stretching dominates completely. Beyond it, no signal emitted now will ever arrive. The future light cone of those regions does not intersect your world line. Causality is severed. This differs from the particle horizon, which marks the furthest distance from which light has reached you so far. The cosmic event horizon concerns the future. It defines what you will never see, even in principle. The existence of such a horizon is not an assumption. It follows from the observed acceleration of expansion. Measurements of supernovae, galaxy clustering, and background radiation all indicate that expansion is speeding up. If that trend continues, horizons become permanent features of space-time. This introduces a finality that feels foreign. There are regions that exist now whose future will never be part of your observable universe. They are not hidden behind dust or distance. They are removed by the structure of space-time. The horizon does not enclose the universe. It encloses you. From another galaxy, a different horizon would apply. Each observer carries their own causal boundary. There is no universal horizon that all observers share. Connectivity depends on location and time. This has implications for what it means to describe the universe as a whole. Global statements about structure and fate cannot be verified beyond the horizon. They are extrapolations grounded in local measurements. The horizon also reshapes time. Events beyond it may unfold indefinitely, but their unfolding has no consequence for you. They are not in your future, even if they exist in time. This creates a separation between existence and influence. Something can exist without any possibility of interaction. Physics allows this without contradiction. The unsettling aspect is not that there are limits, but that the limits are dynamic. As expansion accelerates, the horizon can move inward in co-moving coordinates. Regions that are observable now can cross out of reach. You do not lose them suddenly. Their light becomes increasingly redshifted, stretched, and diluted. Eventually, it fades beyond detectability. The objects do not disappear. They become causally irrelevant. This process does not require catastrophe. It is the quiet outcome of measured expansion. Over long timescales, the observable universe thins. The horizon is therefore not a wall you face, but a condition you inhabit. It is defined by how space evolves around you, not by any barrier in front of you. There is no experiment that can breach it, no technology that can overcome it. The limit is written into the geometry of space-time. What lies beyond the horizon is not unknown because it is far away. It is unknown because it is unreachable now and forever by the rules that govern how information moves. 10. The oldest light you can measure. The cosmic microwave background is not distant in space alone, but in time. It marks a moment when the universe became transparent. Its uniformity suggests a scale of early connection that current expansion makes impossible. When you observe this radiation, you are looking back to an era nearly 14 billion years ago. At that time, the universe was a hot, dense plasma, opaque to photons. Light could not travel freely because it constantly scattered off electrons. Only when the universe cooled enough for neutral atoms to form did photons decouple, beginning a journey that would eventually reach you. The surface you observe is not a spatial object, but a temporal one, a relic of a particular epoch in cosmic history. Its apparent uniformity is deceptive. Across regions that would eventually become separated by billions of light years, the temperature is nearly identical. Measurements show deviations of only 1 part in 100,000. This level of uniformity is surprising because in standard models of cosmic expansion, these regions could not have been in causal contact. Light or other signals could not have traveled fast enough to equilibrate conditions across the vast distances that now separate them. The contradiction is stark. The universe appears coordinated at a scale far beyond what light could have influenced at the time. Causality seems violated, yet the measurements are precise and reproducible. Observations from satellites and ground-based instruments converge on the same numbers. There is no uncertainty about the effect. The data is real. Inflation was proposed to reconcile this conflict. During a brief period shortly after the Big Bang, the universe expanded exponentially, stretching space by a factor of at least 26 in a tiny fraction of a second. What were once microscopic regions were blown far apart, producing the uniformity observed today. This is not speculation to entertain curiosity. It is a necessity imposed by observation. Without it, the measured homogeneity would be impossible. Even with inflation, the implications remain unsettling. The light you measure today has crossed space that was stretched dramatically while in transit. The positions and separations you infer are influenced not only by the source, but by the evolution of the medium it traveled through. The cosmic microwave background encodes the geometry and expansion history of the universe, turning distance into a record of dynamic change. The radiation also shows tiny fluctuations, seed patterns that would grow into galaxies and clusters. These fluctuations are small and random in orientation, yet they imprint the blueprint for all large-scale structure. Observing them, you are seeing both the calm and the instability of the early universe simultaneously. Uniformity at the largest scale, variation at the smallest. The tension between order and emergent complexity. Time itself is woven into the observation. The surface of last scattering is not a place you could visit. It is a moment in the past. Photons arriving now left regions of space that have since evolved unimaginably. Galaxies have formed, moved, merged, or dissipated. The light preserves only the state of the universe when it became transparent, frozen in transit across changing space-time. The cosmic microwave background also defines limits. Beyond it, electromagnetic observation is impossible. Before decoupling, the universe was opaque, preventing any direct measurement. You can infer earlier conditions through models, but they cannot be tested directly. The oldest light is therefore not the edge of reality, but the edge of what can be observed. Its uniformity, measured with extraordinary precision, continues to challenge intuition. The large-scale coherence it reveals suggests a level of early connectivity that current cosmic expansion makes impossible. What you see is a relic, not just of energy, but of a structure imposed on space before the universe was recognizable as galaxies, stars, or planets. In the end, the cosmic microwave background is both a record and a limitation. It tells you how space and matter behaved when light first traveled freely, while simultaneously defining the ultimate observational boundary of the universe. Its light is not merely distant in space, it is unreachable in time, a horizon that can never be crossed. 11. Uniformity that should not exist. Regions of the early universe were never close enough to exchange information, yet they share the same temperature. This is not speculation. It is measured to high precision and remains incompatible with simple expansion models. In the standard view of cosmic expansion, light and other signals travel at a fixed speed. Causality limits the regions that can influence each other. When the universe was a few 100,000 years old, the horizon for causal contact, how far a signal could have traveled since the Big Bang, was tiny. Distant regions, separated by vast distances even then, could not have exchanged energy, matter, or information. They were effectively isolated. Yet measurements of the cosmic microwave background reveal an extraordinary uniformity. Temperatures across regions billions of light-years apart differ by no more than 1 part in 100,000. Such homogeneity is not the result of chance. It reflects an underlying coordination across distances that, according to the physics of light travel at the time, should have been impossible. This uniformity cannot be reconciled with naive expansion models where regions simply drift apart over time. If the universe expanded at a constant rate from a singular origin without additional mechanisms, distant regions would retain independent thermal histories. There would be gradients, inconsistencies, and measurable differences. Observations show none of these. The implication is that some process must have connected these regions or imposed coherence before they became isolated by expansion. Inflation offers an explanation. A brief exponential expansion stretched space so rapidly that regions initially within causal contact were pulled far apart. What once could equilibrate became separated, preserving the uniformity in a context where classical causality would otherwise forbid it. Even with inflation, the result remains unsettling. The observable uniformity does not merely indicate initial proximity. It shows that the universe contains correlations imprinted across scales far beyond any point-to-point communication. It is a constraint baked into space-time itself, not a coincidence of local physics. The light you measure today carries a historical record of coherence imposed under conditions radically different from the present. This also affects how scale is interpreted. Uniformity implies that what appears to be vast separation now was once compressed. Space was not simply empty and static. It was a medium whose metric evolved dramatically over time. When you measure the present distances between structures, you are seeing the residue of processes that operated under entirely different geometrical and causal rules. The observation challenges intuition because uniformity requires an origin not in motion, but in correlation. It suggests that large-scale properties of the universe are constrained by factors independent of local interactions. You cannot derive the uniform temperature of distant regions by looking at stars, galaxies, or clusters individually. It emerges only at the level of the whole. The tension between causality and observation deepens further when considering fluctuations. Tiny variations in temperature exist and are measurable, but they are superimposed on an almost perfect backdrop of uniformity. These fluctuations seeded the formation of galaxies and clusters. They show that uniformity is not absolute, yet the scale of coherence remains far beyond what classical physics would predict. Every measurement reinforces the paradox. Satellites, balloons, and ground-based detectors all converge on the same numbers. There is no instrumental bias that could explain the homogeneity. The universe behaves as though a coordination mechanism operated beyond the causal limits of the early cosmos. The unsettling conclusion is that uniformity is built into the structure of space itself. The early universe was organized in ways that simple expansion cannot account for. This order was preserved while space grew and time passed, leaving an imprint that remains detectable billions of years later. You are confronted, therefore, with a universe that is at once predictable and inexplicably coherent. Large regions, disconnected at the time, exhibit identical properties. The data are real, precise, and unavoidable. The simple expectation that distant parts of the cosmos should have evolved independently is demonstrably false. Uniformity exists where it should not. It is a constraint imposed by the history of the universe itself, silently defying the intuitive limits of causality. 12. Inflation as a measured necessity. Inflation is introduced not to explain the universe aesthetically, but to reconcile measurements. It proposes a period when scale expanded faster than light could traverse, reshaping distances beyond intuitive comprehension. The requirement for inflation arises directly from observation. The cosmic microwave background exhibits uniformity across regions that, in a non-inflating universe, could never have communicated. Without a mechanism that temporarily allowed causal contact and then stretched space dramatically, there is no way to account for the homogeneity measured to extraordinary precision. The effect is not a model preference. It is demanded by the data. During inflation, space-time itself grew exponentially over a tiny fraction of a second. Distances that were once microscopic expanded to macroscopic or even cosmic scales. Light or any other signal could not keep pace with the expansion. In this sense, inflation temporarily broke the classical expectation that causal influences propagate at a finite speed. Regions initially in contact were thrust far beyond one another, carrying the imprint of their earlier interaction into domains that would otherwise be causally disconnected. This expansion is not motion through space in the ordinary sense. Galaxies and matter did not move faster than light locally. Instead, the metric defining the separation between points stretched. Space itself grew. Distances increased without requiring objects to traverse them, and the effect was uniform and isotropic, preserving the large-scale symmetry observed today. Inflation also explains why the universe appears flat. By stretching space, any initial curvature becomes negligible over observable scales. Measurements of the cosmic microwave background and the distribution of galaxies confirm this flatness to high precision. What was once a small, potentially irregular patch of space-time became vast and nearly uniform, producing the conditions we now measure. The necessity of inflation is thus embedded in multiple observations. Homogeneity, isotropy, and flatness, all measurable properties, converge on a single explanation: an early epoch when the scale of the universe expanded faster than the light could travel. Without it, the standard expansion model cannot produce the patterns we detect, yet the concept remains unsettling. Inflation reshapes space on a scale that defies everyday intuition. A region initially smaller than a proton could in an instant encompass distances larger than the observable universe. Our usual understanding of causality and locality breaks down. Space, time, and distance become fluid quantities dependent on the expansion history. The distances you measure today are a consequence of processes that occurred in a regime entirely unlike your local experience. Moreover, inflation implies a past that is both extremely brief and infinitely consequential. Tiny initial conditions are stretched to cosmic significance. Quantum fluctuations present during inflation are amplified, seeding the structures that would eventually become galaxies and clusters. Minute differences in energy density became the blueprint for everything you see, encoded in the large-scale structure of the universe. Inflation is also self-limiting. It ends when the energy driving the rapid expansion decays into ordinary matter and radiation, transitioning the universe into a slower, more familiar expansion. This sets the stage for the epochs we can observe: the formation of atoms, the decoupling of photons, and the release of the cosmic microwave background. Yet the memory of the inflationary period persists in every measurement of distance, temperature, and redshift. The effect on your perception of scale is profound. Distances no longer correspond to linear or intuitive separation. Space itself has been stretched to create the very framework in which measurement is meaningful. The universe you observe today is an expanded record of a brief, intense phase that cannot be experienced directly. Inflation is not an aesthetic idea, a philosophical conjecture, or a speculative narrative. It is a measured necessity imposed by the universe itself. Without it, the observable data, homogeneity, flatness, correlations, and the cosmic microwave background cannot be reconciled. The early universe demanded a rapid reshaping of space, and that demand is written into every photon we now receive, across every region we can measure. In accepting inflation, you accept that distances are not fixed, that space can grow faster than light, and that the universe we inhabit is the stretched outcome of a process both measured and incomprehensible at human scale. It is not just a theory, it is an inescapable consequence of the observations that define modern cosmology. 13. After inflation, space forgets. Once inflation ends, space retains its altered scale without preserving memory of how it got there. Observations can trace its effects, but not the mechanism directly, leaving scale historically altered but causally opaque. The universe emerges from inflation into a regime governed by slower, more conventional expansion. At this point, the rapid stretching has ceased, but its consequences remain imprinted on every region of space-time. Distances that were once microscopic now span billions of light years. Structures that later form, the first galaxies, clusters, and voids, are organized on a canvas reshaped by processes no longer accessible to direct measurement. This forgetfulness of space is not metaphorical. The altered geometry retains no direct record of the violent expansion. There is no marker or artifact that would allow an observer to reconstruct the local metric at intermediate stages of inflation. The universe presents only the outcome, a large, homogeneous and flat region with correlations across scales that cannot be explained by local interactions alone. The mechanism is invisible, leaving only the consequences. You can measure the effects in several ways. The uniformity of the cosmic microwave background, the small fluctuations that seeded galaxies, and the large-scale flatness of space-time all encode the results of inflation. Yet these are indirect. They do not show the process itself, only its necessity. The inflationary epoch is inferred from the present structure of space, not witnessed directly. This has implications for how you define distance and scale. After inflation, space has expanded to a size where conventional rulers are insufficient. Light emitted from different regions must traverse a dynamically stretching medium. When you observe a galaxy, the distance you assign depends on how the intervening space evolved, not on a fixed coordinate system. Scale becomes historically contingent, a product of past processes whose details are causally inaccessible. The universe's forgetfulness also implies a decoupling between cause and present observation. Inflation caused correlations between regions that were later separated by unbridgeable distances. These correlations are measurable, yet the cause of the expansion, the energy and dynamics driving inflation, cannot be observed directly. The universe allows you to infer an effect without access to the agent that produced it. This detachment produces a subtle paradox. You are embedded in a space-time whose structure is the cumulative result of processes you cannot witness. Scale is real and measurable, yet the path that led to it is hidden. Historical change becomes a fundamental component of what you now call space. Geometry carries memory only through its consequences, not through direct traceable events. Local physics continues as expected, but the underlying stage is fundamentally altered. The homogeneity of large regions is preserved, but it is no longer a product of causal contact between parts of the universe. It is a relic of expansion that moved regions apart faster than signals could propagate. The stage is smooth, but the mechanism that created it is invisible. This forgetfulness affects interpretation of all distant observation. The light you receive has traversed a space whose metric changed while in transit. You are not only observing an object, but also the historical stretching of the space between you and it. Distance becomes entangled with past dynamics. Scale is inseparable from cosmic history. The universe, in this sense, is permanently altered. Inflation establishes correlations, stretches space, and defines causal boundaries. Yet, it leaves no direct record. Measurements can map the results, but the mechanism is causally opaque. You can quantify the distances, velocities, and structures that arise, but you cannot reconstruct the precise sequence of space-time expansion. In the aftermath, space behaves as if it had always been this large. The dramatic change is invisible in the present metric, only detectable through careful observation and inference. What you measure is the result of an unobservable history. The universe provides evidence of a transformation without preserving the means to witness it. After inflation, space forgets. It carries the consequences of a process that is essential, real, and measurable, yet fundamentally beyond direct causal access. The structure, scale, and uniformity you observe are the echoes of an event that is gone, leaving a cosmos whose present properties are inseparable from a past that cannot be directly known. 14. Galaxies as tracers, not anchors. Galaxies do not mark fixed positions, they drift with expanding space. Using them as reference points gives the illusion of structure, while measurements show that the grid itself is stretching beneath them. From a casual perspective, galaxies appear as stable islands in an otherwise empty void. Images reveal spiral arms, bright cores, and defined shapes, suggesting permanence. Catalogues of positions reinforce this view. Stars and gas clouds rotate around central masses, while the galaxies themselves are plotted across the sky. These positions seem anchored in a cosmic coordinate system. Observation, however, reveals a different truth. Redshift measurements indicate that nearly all galaxies are receding from one another. The rate of recession increases with distance. This is not a simple motion through pre-existing space, as planets move through the solar system. Instead, the metric defining distance is stretching. The galaxies are effectively embedded in a dynamic lattice that expands beneath them. Using galaxies as reference points creates a conceptual trap. When you measure separations or orientations, the local coherence of clusters and filaments gives the impression of a fixed cosmic scaffolding. Large-scale structures appear as a cosmic web with nodes and strands, suggesting spatial permanence. Yet the web is painted onto a canvas that is itself growing. The apparent stability is a local artifact, persisting only because expansion is negligible across small scales. At intergalactic distances, this illusion collapses. Galaxies separated by millions of light-years move apart faster than light can traverse those distances locally. They remain stationary relative to nearby neighbors, but drift relative to the universal metric. Their positions do not mark fixed points in space. They trace the flow of an evolving geometry. The apparent positions you record are a snapshot, frozen in observation, not a marker of absolute location. The stretching of space beneath galaxies has direct observational consequences. Light traveling from a distant galaxy is redshifted in proportion to the accumulated expansion along its path. The measured redshift encodes both the distance the galaxy would have had in static space and the expansion that occurred during the light's journey. You are not seeing the galaxy where it is now. You are seeing where it was relative to a metric that has changed continuously while the photon traveled. Clusters and superclusters further illustrate this point. While gravitationally bound systems resist expansion and maintain approximate cohesion, the surrounding voids grow. Space stretches in the regions between clusters, making the apparent cosmic web less a fixed scaffold than a pattern overlaid on an inflating grid. The universe's structure is relative, defined not by absolute positions of galaxies, but by the history of expansion. Even within the local group, where gravity dominates, the underlying metric subtly influences relative motion. Proper velocities can partially counteract expansion, but over larger scales, the effect is negligible. Beyond a few tens of millions of light-years, galaxies effectively drift with the expansion, confirming that the grid is active, not passive. This has profound implications for measurement and interpretation. Maps of galaxy positions are snapshots, not absolute charts. Using them as anchors obscures the deeper truth. The underlying space is dynamic, stretching in all directions. Structures are real but embedded in a geometry whose expansion defines their relative separations. The universe is therefore simultaneously structured and fluid. Galaxies trace patterns that reveal the outcome of gravitational and primordial processes, yet they do not fix the coordinates of space itself. Observationally, they are indicators, not rulers. They show you the distribution of matter and the history of density fluctuations, but they cannot serve as immutable points in a static grid. Accepting this redefines your sense of cosmic scale. Measurement is relational. Position, distance, and separation are contingent on the evolving metric. Galaxies are useful for tracing expansion, for calibrating redshift, and for modeling structure formation, but they do not anchor the universe. They drift with it, silently marking both the evidence of past processes and the stretching space that carries them apart. In the cosmos, permanence is local and relative. On the largest scales, galaxies are tracers, not anchors, highlighting the fundamental truth that space itself is not a fixed stage, but a dynamic, historically stretched medium in which all measurement is conducted. 15. Time slows with distance. Distant supernovae do not just appear farther away. Their light curves unfold more slowly. Time itself is observed to dilate with distance, linking scale directly to temporal distortion. When a supernova explodes, it emits light in a characteristic pattern, a rapid rise in brightness followed by a slower decline. Nearby events follow this pattern on timescales that match laboratory expectations. When astronomers observe supernova billions of light-years away, the same pattern persists, but stretched. The rise and decay are slower, as if the universe itself has lengthened the seconds separating photons. This effect is not an artifact of measurement. Spectra confirm that the wavelength of light is redshifted proportionally to distance. The timing of events, measured independently, scales with redshift. Light does not just arrive with longer wavelength, it arrives in a temporally dilated sequence. Every oscillation, pulse, or peak is stretched by the same factor that scales spatial separation. Distance and time are linked. The phenomenon arises naturally from the expansion of space. As space stretches, it not only increases the separation between source and observer, but also stretches the intervals between emitted wavefronts. A photon emitted at one instant reaches you later, relative to the photons that follow. The temporal pattern is preserved, but dilated. Time at the source appears slower when observed across expanding space. This is not merely a relativistic Doppler effect in motion through space. Even galaxies that are locally stationary relative to the expansion metric exhibit this time dilation. The stretching is a property of space-time itself, not of objects moving through it. Temporal intervals are encoded in the geometry, not in local processes. The implications are profound. Observation of distant events does not show a universe simply farther away. It shows a universe in which the flow of time, as measured from your frame, is intertwined with scale. Light curves, oscillations, and periodic phenomena are not absolute markers of temporal passage. They are filtered through a stretching metric. This complicates interpretation. A distant supernova appears to take longer to reach its peak, but the star itself did not experience a slower explosion locally. Its proper time, the time measured at the event, proceeds normally. Only when the event is observed across the expanding universe does time appear dilated. Temporal measurement is relational, dependent on the history of space through which the signal travels. Time dilation links directly to distance measurements. Supernovae serve as standard candles precisely because their light curves can be compared to nearby examples. Observing the degree of temporal stretching provides a cross-check on redshift-derived distances. In this way, temporal dilation is not a curiosity. It is a fundamental aspect of measuring cosmic scale. The effect also emphasizes the entanglement of space, time, and observation. You are not simply seeing a star as it was billions of years ago. You are seeing its history filtered through an evolving space-time, where both intervals of light and distances between objects are altered. Every photon encodes spatial and temporal expansions simultaneously. Even at moderate distances, the cumulative stretching becomes measurable. At extreme redshifts, the effect dominates the interpretation of events. Time, like scale, is no longer independent. It is shaped by the expansion of space and the causal structure of the universe. Observation becomes an interplay between spatial separation and temporal distortion. This also has philosophical implications. The flow of time is not universal. It is local to each region, measured through the transmission of signals. Observers in different locations, separated by cosmological distances, perceive sequences of events with fundamentally different durations, even though each local clock ticks normally. By connecting temporal dilation with scale, supernovae reveal a universe where distance and time are inseparable. You cannot discuss one without reference to the other. Measuring the cosmos is not merely about positions or velocities. It is about the unfolding of time itself across the stretched, dynamic fabric of space-time. Time slows with distance, not metaphorically, not due to perception, but as a measurable, quantitative effect. Every observation of distant light carries within it a record of temporal stretching. Scale and time are intertwined. The universe does not merely extend outward, it elongates the very flow of experience across its vast distances. 16. Dark energy and accelerated separation. The measurements show that expansion is speeding up, not slowing down. The cause is labeled dark energy, not as an explanation, but as a placeholder for a measured effect with no known mechanism. Classical expectations suggested that the gravitational pull of matter should decelerate cosmic expansion over time. Mass attracts, energy curves space-time, and distant objects should gradually slow in their recession. This intuition held until precise observations of distant supernovae revealed the opposite. Faraway galaxies are not merely receding, they are accelerating away from each other, their separation increasing at a faster rate than would be caused by initial expansion alone. The term dark energy was introduced to describe this discrepancy, but it is not a substance that has been directly detected. It is not a field measured in a laboratory or a particle inferred from collisions. It is a parameter that quantifies the observed acceleration. Cosmologists include it in equations to match the measured expansion rate, but its origin, composition, and nature remain unknown. It is the universe signaling a force whose cause is beyond current understanding. The effect is global. Acceleration is not localized to a cluster, filament, or void. It appears in every direction, affecting the entire cosmic metric. Light from distant sources encodes this acceleration, manifesting as redshift that grows faster than predicted by decelerating models. The expansion is embedded in space-time itself, and the influence of dark energy is measurable in the dynamics of the universe on scales far larger than any local, gravitationally bound system. This presents a conceptual challenge. Observations demand a driver for expansion that is pervasive, uniform, and intrinsically repulsive in the sense that it opposes gravity on the largest scales. Yet no mechanism consistent with known physics provides a satisfactory explanation. Vacuum energy contributes a small fraction of what is needed, but the magnitude observed in the universe is far beyond theoretical expectation. The parameter fits the data, but the underlying cause remains causally opaque. The acceleration also redefines the long-term structure of the universe. Regions once accessible to observation will eventually move beyond the cosmic horizon. Light emitted now from these galaxies will never reach you. The universe becomes divided between causally connected zones and regions permanently beyond reach. Not by spatial distance alone, but by the interaction between expansion and light travel. Scale is stretched, time is dilated, and the observable portion of the cosmos shrinks relative to the total. Dark energy influences measurement as much as it influences motion. The interpretation of redshift, distance, and temporal evolution depends on incorporating accelerated expansion. Supernovae light curves, cosmic microwave background correlations, and galaxy surveys all require accounting for the increasing metric. Ignoring dark energy produces contradictions between independent datasets. Its effect is not optional, it is imposed by observation. The unknown nature of dark energy intensifies its unsettling character. Unlike gravity, which has a clear source in mass and energy, dark energy has no direct traceable origin. It cannot be probed locally, it cannot be shielded or measured in situ. Its existence is inferred solely from its influence on large-scale space-time, producing a global acceleration that reshapes every region simultaneously. This makes the universe both predictable and incomprehensible. Expansion follows a measurable pattern, one that allows for accurate modeling of distances, redshifts, and causal structure. Yet the force driving that pattern is fundamentally opaque. You can quantify its effects with high precision, but the underlying physics remains unknown. Measurement confirms acceleration, but explanation is absent. Dark energy also reframes the notion of causality. The expansion it drives is not contingent on local interactions. Galaxies recede not because they are pushed by nearby masses, but because the metric itself evolves. Space is stretching from within, producing separation without apparent local cause. The universe acts globally in a manner that resists intuitive, mechanistic explanation. Observing accelerated expansion is therefore observing a profound disconnect between measurement and understanding. The data is precise, reproducible, and unavoidable. The cosmos accelerates, but why it does so is a question beyond the reach of experiment. Dark energy is a label for this unknowable force, a recognition that the universe behaves in a way that defies direct causal comprehension, leaving the largest scales of reality governed by an effect with no known mechanism. 17. Future scale without access. As expansion accelerates, more galaxies cross the cosmic horizon. Scale continues to increase while the accessible universe shrinks. Measurement loses reach even as space grows. The cosmic horizon is not static. It is a consequence of the interplay between light speed, cosmic time, and the evolving metric of space-time. As expansion accelerates under the influence of dark energy, regions that are observable today gradually move beyond causal contact. Galaxies that now appear as distant points of light will eventually recede faster than photons can traverse the expanding space between you and them. Their light will never reach you, and they will vanish from observation without ever leaving the universe. This process is not instantaneous. The recession occurs over billions of years, but it is inevitable given the measured acceleration. The horizon effectively contracts in co-moving coordinates. Objects that once contributed to the observable universe will fade into permanent unobservability. What you can measure is therefore shrinking, even as the universe itself continues to grow. The implications for scale are profound. distances are no longer just large, they are progressively becoming inaccessible. The measure of the universe you can interact with or study is bounded by a horizon that tightens with time. Expansion is not uniform from the perspective of causal reach. It selectively removes regions from your observational capacity. The universe continues, but your window onto it narrows. This creates a fundamental asymmetry between existence and knowledge. Galaxies, clusters, and structures continue to exist beyond the horizon. Their mass, motion, and evolution proceed according to physical law, yet they are irretrievably disconnected from you. Scale increases independently of observation. The universe grows, but your ability to measure that growth diminishes. Reality extends where measurement cannot follow. The effect also reframes temporal understanding. Observing distant galaxies is inherently looking into the past. As the horizon advances, the past you can observe becomes more limited. Even the light emitted before these galaxies cross the horizon will never arrive. Your accessible history of the universe shrinks along with your accessible space, compressing the dataset on which cosmology depends. This dynamic presents a new challenge to understanding global structure. Measurements of cosmic expansion, density, and large-scale correlations are necessarily restricted to a fraction of what exists. Beyond the horizon, properties may continue smoothly, or they may vary. Observation alone cannot decide. The accessible universe is a subset defined not by distance or mass alone, but by the interaction of expansion and light propagation. Gravitationally bound systems, galaxies and clusters, resist expansion locally, but the space between them continues to stretch. Even objects that remain in causal contact eventually see fewer neighbors. Filaments of the cosmic web thin, and the universe becomes more isolated from the observer's perspective. The growth of scale is paradoxical. The fabric of space stretches, but the observational content diminishes. This also affects predictions. You can model the evolution of structure, but those models rely on the assumption that what you see now is representative of what exists beyond reach. As more regions cross the horizon, the ability to verify these assumptions diminishes. Scale continues, yet confirmation recedes. The universe is expanding faster than your capacity to confirm it. The long-term outcome is a universe that is vast, yet increasingly unknowable. Measurement is not a passive recording of existence. It depends on causal access. As expansion accelerates, the proportion of the universe that is observable approaches a diminishing fraction. The edge of knowledge is defined not by the universe's size, but by the limit imposed by light and expansion. In this context, scale becomes both absolute and inaccessible. The universe grows without bound, yet your observational footprint shrinks. Distance exists where it cannot be measured, time continues where it cannot be recorded, and structure persists where it cannot be traced. Expansion creates a future in which reality extends beyond all possible access, leaving a cosmos whose scale is fully real, but forever partially invisible to those who observe it. 18. The end of large-scale structure. Eventually, only local gravitationally bound systems remain visible. The universe does not collapse or fade, but becomes observationally isolated, its scale inaccessible by any instrument. Galaxies within clusters continue to orbit, stars within galaxies continue to shine, and planetary systems persist. Locally, physics operates as expected. Gravity binds matter into coherent structures that resist the expansion of space. These systems remain observable because the forces holding them together overpower the metric expansion at small scales. Clusters, galaxies, and solar systems do not drift apart due to cosmic acceleration. Beyond these local systems, however, the story is different. The expanding universe gradually removes all distant structures from causal contact. Superclusters that are today visible as faint smudges of light will recede beyond the cosmic horizon. Filaments of the cosmic web, previously connecting clusters across vast voids, will stretch into unreachability. The large-scale structure, the intricate lattice of galaxies, clusters, and voids, will no longer be observable. What remains is a local bubble of gravitationally bound matter surrounded by an empty, inaccessible void. Observationally, the universe becomes a collection of isolated islands. The cosmic microwave background, currently detectable as a faint glow from the surface of last scattering, will redshift into undetectability. Photons stretched by accelerated expansion will fall below measurable energy thresholds, removing even indirect evidence of large-scale coherence. The very signals that once allowed reconstruction of cosmological history vanish from observation. From this perspective, scale itself becomes meaningless in operational terms. While the universe continues to grow, the measurable portion shrinks. Distance between unobservable regions increases without limit, but you can no longer quantify it. Expansion persists, but only locally bound systems remain accessible. Measurement loses its scope, and large-scale structure effectively ends. Not because the universe has changed physically, but because your ability to observe it has vanished. This isolation has profound implications for understanding. Cosmological models rely on observation across vast scales to infer the history, composition, and dynamics of the universe. Once the observable universe contracts to only local systems, these models can no longer be tested beyond the immediate neighborhood. Patterns of redshift, distribution of galaxies, and correlations in the cosmic microwave background are erased from detectable record. The universe remains large, but knowledge of it is effectively reduced to a fraction of its present reach. Time and causality take on a different character. Events in distant regions continue to unfold, but they have no effect on your local environment. Galaxies beyond the horizon may merge, collapse, or form new stars, yet these processes will never intersect your observational frame. The future becomes a domain where existence is decoupled from influence. Scale exists, but only as an abstract property of a universe you cannot probe. Even local structure is framed by this context. Gravitationally bound systems persist, but they are islands in an ocean of unobservable expansion. The relative isolation becomes total. There is no cosmic web connecting one cluster to another in a measurable way. Every measurement of large-scale distribution collapses to the study of what is gravitationally bound. The universe, in practice, appears far smaller than it is in reality. The fading of large-scale structure emphasizes the relational nature of observation. Space continues to stretch, time continues to pass, and structures continue to exist, but their relevance to measurement and knowledge diminishes. The universe's expansion separates existence from observability, leaving only local coherence accessible. This outcome is a direct consequence of the measured acceleration of expansion. Dark energy drives galaxies apart, redshifting light beyond detectability and enlarging distances faster than signals can traverse them. Scale continues independently, but observational access diminishes inexorably. In the far future, the cosmic map contracts to a handful of local systems, while the remainder of the universe grows ever more distant and unknowable. In the end, the universe does not vanish, nor does it collapse. It persists, vast and continuous, but for any observer, its large-scale structure ceases to exist in a measurable sense. The cosmos becomes an isolated expanse of local matter, a silent testament to the tension between real-scale and accessible knowledge. The end of large-scale structure is not a physical destruction. It is an observational horizon that permanently limits the scope of human measurement. 19. Finite observation in an expanding whole. You are limited to finite measurements inside an indefinitely expanding system. This is not a limitation of technology, but of causality itself, embedded in the structure of space-time. Every observation you make is constrained by the speed of light and the expansion of space. Photons emitted from distant sources carry information from their point of origin, but only if the intervening space allows them to arrive. As the universe accelerates, more regions become causally disconnected. Signals that could once traverse space in finite time now fall behind the expanding metric, leaving entire swaths of the cosmos beyond observational reach. The observable universe is therefore a subset of the whole, defined not by physical boundaries, but by the causal pathways that light and other signals can traverse. This finitude is measurable. The cosmic microwave background provides the limit of what you can see of the early universe. Beyond this surface of last scattering, space was opaque to photons. You can infer conditions prior to decoupling only indirectly, using models constrained by present measurements. Beyond that, the universe may continue in ways you cannot detect, yet those regions remain real. Existence is not contingent on observation. Causality merely imposes a limit on access. Expansion compounds this constraint. Distant galaxies recede with increasing speed due to dark energy. Their light, stretched and redshifted, eventually becomes undetectable. The cosmic horizon moves inward relative to co-moving coordinates, continually shrinking the fraction of the universe that is accessible. Measurement loses reach even as space grows. The observable region is not fixed, and every epoch defines a new boundary beyond which information cannot propagate. This produces a subtle but profound separation between reality and knowledge. Structures continue to evolve beyond your horizon. Stars form, galaxies merge, voids expand, and yet all of these events are invisible to any observer confined within the accessible portion. Scale exists independently of observation. The universe grows, but your capacity to measure, map, or interact with it is bounded by causality itself. Measurement is finite even in an infinite or indefinitely expanding whole. The effect also alters how you interpret time. Light arriving from distant sources is delayed not just by distance, but by the history of expansion. You are observing the universe as it was, not as it is. The causal disconnection imposed by accelerated expansion means that even events occurring now in distant regions will never be incorporated into your observational dataset. Future measurement is constrained by the same principle as present measurement. Space itself can prevent signals from reaching you. Gravitationally bound systems provide the only islands of permanence. Clusters, galaxies, and stellar systems remain connected and observable locally. But these regions are embedded in a larger structure that is increasingly inaccessible. Filaments and superclusters, once traces of large-scale cosmic structure, eventually drift beyond reach. the universe becomes a set of isolated, self-contained systems, each observable only from within its local domain. This imposes a fundamental epistemological limit. Cosmology relies on observations across space and time to infer the laws governing the whole. As expansion accelerates, these inferences become increasingly reliant on extrapolation from the finite subset you can observe. The universe continues indefinitely, but your knowledge of it is necessarily restricted. Observation is inherently partial, bounded by the interplay of space-time geometry and the causal structure embedded within it. Even the measurement of expansion itself is constrained. Redshift, supernova light curves, and cosmic microwave background correlations all trace the history of regions still visible. Beyond the horizon, acceleration continues unmeasured. The universe may contain complexity, inhomogeneity, or structure that will never influence your accessible frame. Knowledge is finite, while existence remains unbounded. Ultimately, finite observation in an expanding whole is not a technological problem. No telescope, no detector, no method can extend your reach beyond the constraints set by the universe's geometry. Measurement is limited because causality is absolute. The universe is indefinitely large, yet your capacity to record, verify, or interact with it is fundamentally restricted. Every measurement captures only a fragment, leaving the remainder real but forever beyond reach. This reality imposes a quiet tension. The universe continues to grow and evolve, but observation cannot follow. Scale and structure exist where they cannot be confirmed. Space, time, and matter proceed independently of measurement. The cosmos is vast and inexorably expanding, yet for any observer it remains a finite stage, bounded by the limits of causality, embedded in the fabric of space-time itself. 20. Geometry. Without intuition. On cosmic scales, space may be flat, curved, or effectively infinite. Measurements suggest near-perfect flatness, which paradoxically implies either infinite extent or finely tuned conditions. The geometry of space is determined by the relationship between distances, angles, and volumes on large scales. In a flat universe, the rules of Euclidean geometry apply. Parallel lines remain parallel, triangles add to 180 degrees, and the ratio of a circle's circumference to its radius is constant. Observations of the cosmic microwave background, combined with surveys of galaxy distributions, indicate that, to high precision, the universe behaves as if it is flat across the observable volume. This is unsettling because flatness on cosmic scales is not a trivial result. Any deviation in the early universe, whether through curvature induced by excess mass or a lack thereof, would have been amplified by expansion. Positive curvature would lead to eventual reconvergence of geodesics, creating a closed, spherical-like geometry. Negative curvature would produce diverging paths and a hyperbolic structure. Yet, measurements find that neither occurs. Space behaves as though it is perfectly balanced at a critical density, where gravitational attraction and expansion counteract exactly. Flatness implies extreme fine-tuning. The density of the universe must have been within a tiny fraction of the critical value shortly after the Big Bang. Any significant deviation, even minuscule, would have led to large-scale curvature observable today. The precision required approaches 1 part in 10 to 60. This is not an artifact of measurement error. It is a fundamental constraint imposed by the structure of space-time. The universe we observe exists in a state that is highly improbable, without an underlying mechanism enforcing it. Inflation provides a resolution, but in doing so, it produces its own unsettling implications. A brief period of exponential expansion can stretch space to such an extent that any initial curvature is flattened almost entirely. In this view, flatness is not coincidental, but a consequence of the dynamics of early expansion. However, the scale produced by inflation is so vast that even the observable universe represents only a tiny fraction of the total. The implication is that beyond the horizon, space could continue indefinitely, effectively infinite, yet forever inaccessible to measurement. The paradox deepens when considering observational limits. Flatness suggests that parallel lines do not converge or diverge, but this conclusion is based only on the portion of space accessible to you. Beyond the observable horizon, geometry could deviate without ever affecting measurements made within your causal domain. Your perception of flatness is therefore both precise and limited, a local measurement with implications that extend to a scale you cannot access. Flat geometry also interacts with other cosmological observations. Accelerated expansion, dark energy, and the distribution of large-scale structure all rely on assumptions about the underlying metric. The measurement of distances, redshifts, and cosmic microwave background fluctuations presumes a flat geometry, which then constrains the inferred evolution of the universe. Observables are intertwined with the global geometry, making every conclusion dependent on the assumption of flatness extending beyond the horizon. Yet, flatness on such scales challenges intuition. Human experience is rooted in local curvature, from hills and valleys to planetary surfaces. Extrapolating that intuition to billions of light years produces a cognitive dissonance. The universe is vast, nearly uniform, and yet balanced with a precision that defies expectation. It is flat in a way that suggests either infinite scale or an almost impossible alignment of initial conditions. The implications are profound. Either the universe extends without bound, containing regions that will never be observable, or it is finite but arranged in an exquisitely precise way. Both possibilities strain the intuition built from local experience. Measurement confirms flatness. Observation supports it across the observable domain. But beyond that, scale, curvature, and structure enter the realm of inference, where certainty is bounded by causal limits. Geometry on cosmic scales is therefore divorced from everyday understanding. Flatness is measured, real, and pervasive, yet it carries consequences that stretch beyond direct access. Space behaves predictably according to mathematics, but the magnitude and extent of that space surpass intuition. The universe is balanced on a knife edge between infinite expanse and improbable fine-tuning, revealing a structure that is simultaneously comprehensible and deeply counterintuitive. 21. Infinite space, finite information. If space is infinite, information remains finite within your horizon. Scale increases without adding accessible content, separating physical extent from experiential reality. The observable universe is bounded not by edges in space, but by the causal limit imposed by light travel time and the expansion of space-time. Beyond this horizon, galaxies, clusters, and structure may continue indefinitely, but they are beyond any possibility of observation. The universe can be vast, even infinite, yet your access to it is necessarily limited. Information, the raw data about positions, velocities, radiation, and structure, exists only within a finite sphere surrounding you. The remainder, no matter how extensive, remains operationally unknowable. This creates a profound separation between scale and measurement. Space can extend without bound, yet each new increment in distance adds nothing to your experiential dataset once it passes beyond the horizon. The metric grows, the separation between distant objects increases, and light from ever more remote regions fails to reach you. Reality continues, but your awareness and interaction with it are confined to a finite subset. Observational cosmology is therefore intrinsically partial. Every measurement describes only a fraction of existence, bounded by the limits of causality. The expansion of space compounds this limitation. Accelerated separation driven by dark energy ensures that even regions currently observable will eventually recede beyond reach. Structures that once contributed to the large-scale picture, superclusters, filaments, voids, will disappear from observation. What remains accessible are only gravitationally bound islands, the local group, nearby clusters, and their constituent galaxies. The vast majority of the universe, while real, becomes irrelevant to any empirical account. Information is finite not only in space, but also in time. Photons carry a history of distant events, but only those emitted within a causal window reach you. Events occurring outside this window leave no imprint on your local frame. Future changes beyond the horizon, mergers, collapses, new star formation will never be recorded, never measurable, and never confirmable. Even as space expands, the total information available for study and understanding is capped, locked within a spherical volume defined by the horizon. This distinction between physical extent and accessible content is unsettling because it challenges assumptions about comprehensiveness. The universe may continue endlessly, but observation cannot keep pace. Every catalogue of galaxies, map of the cosmic web, or measurement of the cosmic microwave background represents only a fraction of the whole. Infinity exists in principle, but information is strictly finite, tethered to what can causally interact with your location. Finite information within infinite space also constrains knowledge of global structure. You can measure density, curvature, and expansion locally, but the larger scale patterns beyond the horizon remain speculative by necessity. Any assumption that what is observed within reach is representative of the total universe is an extrapolation, not a direct measurement. The universe continues beyond the observable boundary in ways that are inaccessible to empirical confirmation, leaving scale and existence partially decoupled from knowledge. Temporal and causal separation further intensifies this effect. Observed events are always in the past, filtered by light travel time. Accelerated expansion ensures that many regions will remain forever in the unobservable future relative to your current frame. The flow of time across inaccessible regions continues independently, carrying information that you can never access. Existence unfolds beyond the horizon, unrecorded and untouched by any measurement you can perform. In effect, the universe separates its physical reality from experiential reality. Space may be infinite, containing structures, processes, and matter far beyond comprehension. Yet within your causal sphere, measurement is finite. Scale can grow, distances can expand, but the informational content you can ever acquire remains bounded. This uncoupling forces a profound recognition. The universe is larger than knowledge, more expansive than observation, and ultimately inaccessible in ways that cannot be overcome by technology or ingenuity. The cosmos continues without limitation, but your capacity to measure, map, or understand it is inherently finite. Infinite space exists simultaneously with finite information, embedding a tension between reality and perception, between existence and measurement, between what is and what can ever be known. 22. The scale where meaning breaks at sufficient distance. Scale loses operational meaning. You cannot assign size to regions you cannot observe, measure, or causally interact with, even if equations allow them. Mathematical models can describe space at arbitrary distances, extending beyond the observable horizon into realms that may be infinite. Cosmological equations permit the calculation of volumes, densities, and separations at scales vastly exceeding what can ever be measured. Yet these numbers, though internally consistent, do not correspond to empirical reality. Assigning a physical size to a region requires causal contact. Signals, light, or influence must be able to traverse the space in question. Beyond the horizon, such contact is impossible. Distance is defined mathematically, but not operationally. This disconnect emerges from the interplay between expansion, light speed, and the finite age of the universe. Galaxies receding beyond the cosmic horizon emit photons that will never arrive. Their motions, composition, and evolution continue, yet they are forever beyond measurement. Equations can describe their positions, velocities, or separation in co-moving coordinates, but these descriptors carry no empirical content. Scale, in this context, becomes a theoretical abstraction rather than a meaningful property of the universe. Even for regions marginally beyond reach, meaning begins to degrade. Light from extremely distant galaxies is redshifted to energies below detectability. Time dilation stretches events such that the duration of observable phenomena grows without bound, making measurement increasingly impractical. The further a region lies, the less operational significance its scale holds. Distance is no longer a proxy for interaction or comprehension. It is a number detached from experience. This phenomenon also reframes how structure is understood. Large-scale patterns, clusters, filaments, voids, exist beyond your observational domain. You can extrapolate their existence based on local statistics, but confirmation is impossible. The larger the scale, the more speculation underpins the interpretation of structure. Scale becomes a concept divorced from empirical constraint, a useful mathematical tool, but one that ceases to correspond to anything you can physically test. Causality imposes a hard boundary. Measurement requires signals to cross space. Where this fails, scale ceases to relate to operational reality. A galaxy may occupy a calculable volume, yet that volume has no measurable meaning. Light emitted from that galaxy will never arrive, and no interaction can ever establish its size or distance in a physically verifiable way. Beyond the causal horizon, scale exists in a formal sense, but not in any way that impacts observation or experiment. This break between mathematical description and observable consequence is further amplified by acceleration. Dark energy ensures that the horizon is shrinking in conving coordinates. Regions that might have been reachable in the distant future are already committed to permanent disconnection. The scale of the universe continues to grow, yet the fraction accessible to measurement diminishes. The meaningfulness of any large-scale distance becomes provisional, contingent on what lies within the horizon at a given epoch. Even conceptual tools struggle at these scales. Terms like size, distance, and extent carry operational meaning only when grounded in potential observation. Without the possibility of interaction, these measures become abstract. A structure spanning billions of light-years may exist in calculations, but its scale has no effect on local dynamics or measurable phenomena. Physical meaning breaks down. This also influences the interpretation of infinity. If the universe is infinite, then most of it lies beyond observation. The vast majority of cosmic scale exists where operational meaning is absent. Expansion separates measurable regions from the rest of space, leaving a universe that is both physically vast and empirically restricted. Infinity is defined in theory, not in experience. At the largest scales, the universe becomes a set of formal relationships rather than measurable entities. Equations can extend distances, calculate curvature, and predict evolution. Yet these constructs do not restore meaning where observation is impossible. Scale survives as a concept, but it loses its connection to causal, operational reality. In the cosmos, beyond a certain threshold, size ceases to matter because it cannot be measured, interacted with, or confirmed. Reality continues, but your ability to assign significance to it vanishes. 23. Your position without privilege. Observations suggest no special location. Any observer would measure the same expansion. Scale is not centered on you, yet your measurements define everything you can know. From Earth, the night sky appears as a fixed dome of stars. Constellations, planets, and nearby galaxies form a familiar pattern, and it is tempting to imagine that this perspective carries special significance. Modern cosmology, however, demonstrates that this intuition is misleading. The universe is homogeneous and isotropic on the largest scales. No point in space is privileged, and the metric governing expansion applies uniformly in every direction. Observers located anywhere would measure the same Hubble flow, the same cosmic microwave background, and the same large-scale structure statistics. Your location is therefore not central in any physical sense. There is no cosmic center from which everything recedes, no privileged vantage from which distances are absolute. Expansion occurs equally in all directions relative to any observer. Galaxies appear to move away from you, yet an observer in a distant galaxy would perceive the same recession of other galaxies, including your own. The universe has no geometric center. Its growth is intrinsic to space itself, rather than emanating from a particular point. Despite this absence of centrality, your measurements define your reality. Every distance, every redshift, every time interval is framed relative to your position. The cosmic horizon, the limit of what can be observed, is centered on you, not because the universe has chosen a reference frame, but because causal accessibility is inherently local. What you measure establishes the boundaries of knowledge. Beyond these boundaries, scale, structure, and evolution are conjectured, inferred from models that extend observations outward, but never directly confirmed. This creates an unusual tension. You are unprivileged in the cosmos. There is no absolute center, no absolute scale anchored to your position. Yet all operational understanding, the empirical map of the universe, the reconstruction of its history, the determination of expansion rates, is built from your vantage point. The universe may be infinite, isotropic, and homogeneous, but your horizon defines the limits of certainty. Observation and knowledge are inherently local, even as the universe itself has no local bias. The consequences extend to how scale is interpreted. When you measure redshift, you infer distances and velocities relative to your frame. The Hubble law relates recession speed to distance from your location. but the same law holds true for observers elsewhere. Scale is relational. It exists in reference to each observer's position and measurement, not as an absolute property of the universe. The physical distances between galaxies are not fixed points in a universal coordinate system. They are expressed through an evolving metric relative to the observer. Even the apparent uniformity of the cosmic microwave background reflects this principle. Its isotropy is measured from your position, yet a distant observer would see the same temperature distribution across the sky in their own frame. Scale, expansion, and causal connectivity are always relative to the observer, highlighting that measurement is local even when the underlying geometry is global. Your observations are not privileged physically, but they are epistemically privileged. They define what is known and what remains beyond reach. Causality reinforces this asymmetry. Signals travel at finite speed, and expansion ensures that many regions will never be accessible to you. Every point in the universe has its own horizon, and the intersection of these horizons is limited. Your position determines the data set you can collect, the structures you can confirm, and the cosmological history you can reconstruct. All other regions, while equally real, are effectively hidden from empirical scrutiny. This tension between non-privileged location and observational centrality defines the cosmic condition. The universe has no center, no favored point, yet each observer is surrounded by a sphere of accessible reality. Scale and expansion are universal phenomena, but knowledge is local. Your measurements encode the totality of what can be known, even though physically your position is nothing more than one of countless, equally valid vantage points. Ultimately, every understanding of the cosmos begins with this local perspective. The universe is objectively vast, isotropic, and uncentered, yet your experience, constrained by horizons, causality, and measurement, defines the operational scale of reality. You exist in a cosmos where your position is ordinary, but your observational frame is inescapably central to everything you can know. 24. Measurement as a boundary. Every scale discussed is inferred from signals that reach you. The universe beyond those signals may exist in full accordance with models, but remains unmeasured and therefore structurally incomplete to you. Observation is always local. Photons, neutrinos, gravitational waves, and other messengers travel to your instruments along causal paths defined by the geometry and expansion of space-time. What arrives is filtered through distance, time, and the stretching of space itself. Every measurement is therefore an interpretation of signals that have successfully navigated these constraints. Beyond this sphere, structures may continue. Matter may exist in familiar or exotic configurations, yet none of it contributes to your empirical map. The universe is only partially realized in operational terms. Even vast regions that calculations suggest must exist are only hypothetical until confirmed. The large-scale distribution of galaxies, the network of filaments, and the empty voids are inferred from observations within the observable horizon. Models extend these patterns into unmeasured regions using assumptions of homogeneity and isotropy, but these are not direct measurements. You can predict what exists beyond the horizon with high confidence, yet prediction is not the same as observation. There is an intrinsic boundary set by measurement itself. Scale beyond that boundary exists in principle but is epistemically incomplete. Causality reinforces this limit. The finite speed of light and the accelerating expansion of space ensure that some regions will never be observable. Signals emitted now from distant galaxies may never reach you. structures forming beyond your horizon are physically real, yet permanently inaccessible. No instrument, no experiment, no technological advance can circumvent the causal boundary imposed by the expanding metric of space-time. Your knowledge is confined not by ingenuity, but by fundamental physical law. This principle applies to both space and time. Observing distant objects is simultaneously observing the past. Photons carry historical information. They do not reflect the current state of the emitting source. The combination of temporal delay and expansion means that even regions now within reach may reveal only partial histories. Every measurement encodes a delayed narrative, and every unobservable region represents a missing chapter in the story of the universe. The scale you assign is therefore both spatial and temporal, bound by what signals can reach you. Gravitationally bound systems form the only exceptions, remaining accessible because their internal dynamics counteract expansion locally. These islands, whether galaxies, clusters, or planetary systems, are fully measurable in principle. Yet they constitute only a tiny fraction of cosmic volume. The vast majority of the universe remains effectively unmeasured, leaving your operational understanding dominated by the local and causally accessible. Measurement thus defines the horizon of meaningful scale. Even cosmological constants and inferred parameters are constrained in this way. The Hubble constant, dark energy density, and matter distribution are determined from what can be measured. They are extrapolated to apply globally. Beyond the observable universe, these parameters may hold, but verification is impossible. Your scale is operationally complete only within the bounds of causality. Beyond that, structure, motion, and evolution are theoretically consistent, but empirically undefined. The epistemic consequence is unavoidable. The universe can be vast, infinite even, yet your understanding is finite, framed entirely by the reach of measurement. Scale, structure, and history all depend on the ability of signals to propagate. Where signals cannot travel, the universe exists but remains incomplete in operational terms. This boundary is not artificial. It is embedded in the physics of space-time itself. Thus, measurement does more than quantify the universe. It defines it in practice. Every distance, velocity, or structure becomes meaningful only through observable signals. The unmeasured universe exists beyond comprehension, fully real, yet structurally incomplete from your perspective. The boundary imposed by measurement is absolute. The universe may extend without limit, but for every observer, its scale, history, and form are only partially accessible, forever constrained by the signals that happen to reach them. 25. The edge that is not an edge. The cosmic edge is not a place you could approach. It is a limit imposed by time, expansion, and light. The true scale of the universe is not hidden far away. It is inaccessible by definition, revealed only through the constraints of what you can measure. You might imagine an edge as a boundary in space, a wall, a horizon, or a transition to nothingness. In reality, the universe has no such physical terminus. There is no solid frontier where space ends. Instead, the limits you perceive are determined entirely by the interplay between the finite age of the universe, the speed of light, and the metric expansion of space. The edge is causal, not material. It is the boundary where photons, gravitational waves, and other signals can no longer reach you. Beyond it, existence continues, but observation cannot follow. The cosmic edge is therefore both absolute and relational. It is absolute in that no signal from beyond it can ever intersect your location. It is relational because every observer experiences their own edge, centered on their position. What lies beyond one horizon may be within another's reach, yet for you, it is inaccessible. Scale, in this sense, becomes local. The universe's total size may be infinite, but the portion that can be empirically defined is always finite, bounded by the horizon dictated by your causal frame. Expansion exacerbates this inaccessibility. Accelerated expansion ensures that more distant galaxies will cross the horizon over time. The edge is not static. It moves inward in moving coordinates, even as the universe continues to grow. Regions that are today observable will eventually vanish from view. Light emitted now from these galaxies will never reach you. The universe is expanding faster than you can measure it. In this context, the edge is not a feature of space, but a manifestation of the limits of observation itself. The consequence is that scale cannot be separated from measurement. You cannot assign an absolute distance to regions beyond the horizon because no interaction can verify it. Equations may extend indefinitely, predicting volumes, densities, and separations, but these remain abstract. Operationally, they are disconnected from reality as you can experience it. The farther a region lies, the more scale is divorced from observation. The edge exists where causality terminates, not where space physically ends. This boundary also reframes the nature of structure. The cosmic web, filaments, clusters, and voids are all measurable within your horizon, but beyond it, they continue unobserved. Patterns you perceive, regularities in density, or correlations in the cosmic microwave background reflect only a fraction of the whole. What lies beyond is consistent with models, yet empirically absent. The universe is complete physically, but incomplete observationally. Its scale is real, but your knowledge of it is intrinsically partial. Time compounds the inaccessibility. Observing distant objects is observing the past. Light from the farthest reaches is delayed by billions of years, stretched by expansion. By the time a signal reaches you, the emitting region may have evolved or drifted farther beyond the horizon. The cosmic edge is therefore not merely spatial, it is also temporal. Measurement is always historical, and future portions of the universe will continue to lie beyond reach, irrespective of technological progress. Even the notion of infinity intersects with this boundary. If the universe is unbounded, then the edge is purely a horizon of knowledge. Infinity may exist physically, but your observational footprint remains finite. Scale increases without adding accessible content, leaving a universe that grows while your experiential domain contracts relative to it. The cosmic edge is simultaneously everywhere and nowhere. It is defined by what you can measure, not by what exists. Ultimately, the cosmic edge dissolves the distinction between distance and accessibility. Space continues beyond, structures persist beyond, and expansion carries reality onward. Yet for any observer, the universe is bounded by the signals that can reach them. The edge is not a place to approach. It is a horizon imposed by the limits of causality, light, and expansion. The true scale of the universe is unknowable in any absolute sense. It exists beyond measurement, revealed only through the recognition of the boundaries imposed by observation itself.